Hello and welcome to the IRI seminar series from the Institute of Advanced Research in Artificial Intelligence. I have the great pleasure of introducing today's distinguished speaker, Melanie Mitchell. Melanie Mitchell is the Davis Professor at the Santa Fe Institute. The Santa Fe Institute is dedicated to the multidisciplinary study of the fundamental principles of complex adaptive systems, including physical, computational, biological, and social systems. Melanie wrote her PhD in the research group of Douglas Hofstadter, the author of Gödel-Escherbach. The members of the research group called themselves Fargonauts for Fluid Analogies Research Group. During that time, she developed Copycat, modeling creative analogical thinking in letter strings. She is a self-declared analogy nerd. Melanie is the author or editor of 6 books and numerous academic papers in the fields of artificial intelligence, cognitive science, and complex systems. To name just 2 of her books, the award-winning book Complexity: A Guided Tour, and her latest book is Artificial Intelligence: A Guide for Thinking Humans. In her recent papers and blog posts, she asked why AI is harder than we think and whether GPT-3 can make analogies. The title of her talk is Abstraction and Analogies Are the Key to Robust AI. Really looking forward to this talk on abstraction and analogies and what it means for current scientific practice in AI and ML. Without further ado, I leave the floor to you. Looking forward to this talk. Hand it over to you, Melanie.
Thank you, Christian. Thank you so much for inviting me. I'm going to talk about abstraction and analogy, which I think are really the keys to robust AI. Most of you probably are familiar with the summer research workshop on artificial intelligence proposed back in 1955 by McCarthy and other pioneers of AI. They were very ambitious. They proposed a summer, what they called a 2-month, 10-man study, in which they would try to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. Well, obviously, all of these things are still open questions in the field, but the most understudied and I think most important question is how to get machines to form abstractions and concepts. So we have had a revolution over the last couple of decades in the form of deep neural networks, of course, and they have done amazing things, including revolutionized computer vision, starting with the ImageNet object recognition competition. And in that competition, which started before the revolution in deep learning, here's a plot of the best program and its error rate on that corpus of object recognition problems. And in 2012, of course, the first deep neural network was entered and the error rate was dramatically decreased. And over the years, as the networks became deeper and deeper, the error rate decreased even more until it was below this estimate of human performance on this data set. But the real question, though, for computer vision and similar incredible results in things like speech recognition, language processing, language generation, robotics, and so on, is that what exactly are these machines learning? Well, sometimes what they're learning is fairly surprising. Here's an example from my own lab where one of my former graduate students trained a deep neural network to distinguish photos of animals with photos that did not contain animals. This was from a large nature photo repository. And the neural network did very well on this task. But when my student kind of looked under the hood of what was going on, he found that in large part, what the neural network had learned was to focus on the backgrounds. And the presence of a blurry background was a good predictor of an animal in the photo because most of the animals were in the center and the photographer's focusing on the animal. So the background's blurry, whereas in no animal photos, they're landscapes, and so the background is clear. So this is often called a shortcut in machine learning. It's a common phenomenon where the machine is learning some cue that allows it to do quite well on a particular data set, but the statistical correlations don't always carry over to the general case. Another example of this kind of thing was when a group tried to take a deep neural networks that performed well on web images scraped from the web, like those in the ImageNet data set, take the same categories, but have the photos be taken by a robot with a camera moving around a household. So they took a few of the same categories from ImageNet, took photos from both web scraped images and from the robot images. And when a network was trained on the same kind of data, it was tested on the same kind of data it was trained on, all of these deep neural networks performed very well. This is the accuracy between 0 and 1. But when that same deep neural network was trained on data scraped from the web, but tested on the same categories of photos taken by the robot, the performance went way down, meaning that these photos of the categories of objects were in some sense out of the distribution of what the network had learned from its web-based data. So the deep neural networks were focusing on some features of these images that were not general, that were not the same kinds of features that people focus on. This has been shown in many ways. This particular paper showed that a deep neural network that is able to accurately recognize images with very high confidence, this 1.0 is the confidence with which it's recognizing this as a school bus. But if the researchers Photoshop these objects into strange poses, the neural network is now very confident that it's seeing different categories like a garbage truck or a punching bag, or here where it recognizes a fire truck or a school bus, it's now thinking that it's a school bus with 98% confidence, fireboat, a bobsled. So again, this just shows that these networks are using certain non-human-like features to recognize these objects. This was also shown in a different domain, in the domain of reinforcement learning, where a deep Q learning network, like the one that DeepMind used to learn to play Atari video games at higher than human performance, when it was trained on one of those games, Breakout, and was able to surpass human performance on this game. Breakout's a game where you move a little paddle, here this red paddle, to hit a ball, to collide with bricks, these bars of bricks up here. When the researchers tested this same neural network on version of the game where the paddle was shifted up by a few pixels, it was unable to do well at all. So it's somehow learned certain features of the pixel configuration here that allow it to do well on this version, but it was not able to transfer its knowledge to this really similar version where a human would have no trouble at all. And we've all seen these kinds of adversarial attacks on vision systems. For example, putting some stickers carefully arranged on a stop sign can force a deep neural network vision system to perceive this as a speed limit 80 sign with high confidence. So it seems that what networks are learning is more akin to perceptual categories rather than concepts, the kinds of rich concepts that humans learn that are very robust. And so this is the kind of difference between the more brittle and vulnerable things that networks learn versus what humans are perceiving. So Lawrence Barsalou, a well-known cognitive psychologist, defined a concept as a competence or disposition for generating infinite conceptualizations of a category. That is, a concept is a generative model. It's a way of taking a category, like for example, any of the ImageNet categories that you like, a dog, a cat, a truck, a school bus, and being able to generate examples of it. It's more of a generative than a discriminative model. So one example, is the notion of bridge. You could imagine a deep neural network learning to recognize bridges from many examples, but they would not learn the more robust idea of bridge that humans have that allow us to generalize, for example, to this kind of bridge, which is a kind of an inversion of a normal bridge. This is in which boats cross this water bridge that goes over a highway, or to recognize something like this as a bridge, where ants are being able to cross a gap by creating a bridge with their bodies, or the notion of bridging your hands, or the bridge of a nose, or the bridge of a song. So this is a way that we humans are able to take a concept and generate not just concrete examples of it, but more abstract and even metaphorical versions, and to understand those quite easily. And you can go further, more abstract, talk about bridging the gender gap. I noticed that Joe Biden described himself during his presidential campaign as a bridge to a new generation of leaders. And we understand that instantly without even noticing how abstracted it is from the concrete notion of a bridge. And you can just go on and on. There's so many examples. And bridge is not the only concept that has this generative property. It's really all concepts. So while Barcelou described concepts as being able to infinitely generate examples, Hofstadter described a concept as a package of analogies. And I like this definition also because it really shows how, when we're extending the notion of a bridge or any other concept, we're really making analogies. We're taking the concrete example and we're making analogies to more abstract examples. And analogy is really the driving force behind our ability to abstract. So the question is, how can we get machines to learn concepts in this very more human-like, rich way, rather than the more shallow perceptual categories? And how do we get them to make analogies? So what I'm going to do in this talk is to talk about some of the AI methods that people have developed and the domains they work in for studying this phenomenon of abstraction and analogy. I'm going to talk about 3 different domains, and then talk about how we might make progress in this area. So I'll start with the deep learning systems on Raven's progressive matrices. So you may have heard of Raven's progressive matrices. They were originally created decades ago as a kind of human test of abstraction and analogy making. The idea is that you have this matrix of figures, a 3x3 matrix where the last entry is blanked out and you have to select from a set of possible answers. So here you can see that there's something varying along the rows and the columns. And we can see that there's like this vertical bar that is varying in color and orientation. And there's also an underlying shape that's varying in what the shape is. And you can see after some study that the answer here should be 5. Here's another one. So here we can see that, we're taking the first 2 in a row and combining them to create a third, and that the answer here should be number 8. These problems were first created by a psychologist named Raven, who created hundreds of these problems and used them as a kind of IQ test for people. Psychologists have said that performance on these Raven's problems is highly correlated with intelligence. That's controversial. I'm not going to argue about what that means, but rather talk about how people in AI have adopted this domain to get AI systems or machine learning systems to perform abstraction using deep learning. So here's kind of a little history of that. So here's how you might use a deep learning approach. You would take the 8 figures in the matrix plus the 8 possible answers and use them as just the pixels of those figures as input to a deep neural network. And the goal is to generate a probability distribution over the 8 possible answers so that the network can pick the highest probability one, and that one will be correct. Well, Raven, the original psychologist who created this domain, only created hundreds of these problems for humans. But as you know, deep learning approaches need lots of data to be trained. And so people decided they would generate Raven's problems automatically. So this particular data set, Raven with capital letters, was generated by a group who used a stochastic grammar, kind of an image grammar, where they had a certain number of primitive shapes and colors and range of sizes and other attributes, and would choose layouts and attributes stochastically to be able to generate any number of these problems. And they were able to they generated a benchmark data set that had 42,000 training examples and 14,000 test examples. So now people started applying their deep neural networks to train and test on this domain. So just a few examples, in this domain, you can have problems that, for instance, monotonically increase the number of objects, or have some kind of inside-outside structure here, or and here, you can see that you have the same shape inside as outside. Here we have a system where we're varying the number of the inside objects, monotonically decreasing them, and so on. And so in 2019 in CVPR, this data set was published, and also the researchers tried out different versions of deep neural networks, which I won't go into the details here, and they also tested humans using a crowdsourcing platform, and found that the deep neural networks were yet still quite far away from human performance. And these are all different types of problems, and these are the average accuracy. But of course, once you have a benchmark data set, people improve on it rapidly. So even the same year at the NeurIPS conference, a group showed that their deep neural network was able to surpass humans on this data set, and even more surpass them here the next year, and so on. However, remember I talked about shortcuts in machine learning. Well, in 2020, another group showed that there are actually shortcuts in the Ravens data set. The way that the answers were generated unintentionally allowed a system to just view the answers and be able to solve the problem. So the way that the answers were generated was that the correct answer was taken, and one attribute was modified for each of the 7 other possible answers, which allows a system to be able to just take the answers and look for the majority along each attribute. So here we have the shape. The most common shape is a pentagon. The most common color is black, and so on. And you can choose the answer without even looking at the context matrix. So this was a big problem. Even after a lot of people had published results, it was shown that this data set was biased in this way. This is a train on candidate answers only. You can still do just as well. Okay, so then this group proposed a fix, which fixed that particular bias and showed that then just training on answers alone gets you back to the random choice accuracy. Okay, so now, again, we're back to below human accuracy on this new fixed data set, but the same story happens again. We get improvements. 2020, somebody shows that on this balanced Raven data set, they've now surpassed humans, and surpassed humans even more, and surpassed humans even more. Okay, so we're back now to the question, what did these machines learn? Did they actually learn abstract visual reasoning, or abstract reasoning, or analogical reasoning? This is what these papers are claiming, but to my mind, they haven't really proved it. Do they actually learn abstract concepts? Well, so I did a study with my intern, Victor Odard, who's been working with me this year, to evaluate these systems using what we call concept-based evaluation. That is, instead of just taking a training data set and dividing it randomly into a training set and a test set, assuming some kind of, IID distribution, we do a different kind of evaluation. We identify what are some of the underlying concepts in the test examples, and then ask, given variations on that concept, is the system robust to being able to recognize or understand the concept in its many possible instantiations? So for example, we took a concept we called sameness, where the simplest version for the Raven data set is just everything's the same along each row. Okay, but you can make variations on that where some things vary, there's some differences, but the underlying sameness is the shape, or the color, or the size. And you can vary sameness along different dimensions here. Same number, same number here, same number inside, same angle, and other kinds of sameness. A second concept we looked at is monotonic increase or decrease, where we have like 1, 2, 3, 1, 2, 3, 3, 4, and then the answer would be the one with 5. Or monotonic increase or decrease, say, in shade of gray, or in number of sides on the objects. And you can vary these concepts. Here's the variation in color, number of sides, again, and you can vary these in different ways. So you get the idea. So we created manually, as a proof of principle, the sameness, 210 sameness variations and 80 monotonic increase or decrease problem variations that had a range of sort of complexity. All of them were designed to be relatively easy for humans. And we looked at 2 trained models that had done better than humans on the original Raven data set. Okay. And we said, what if we now test them on these concept-based evaluations? Okay. Well, we found that their generalization on sameness, their accuracy along these concept variations was only 62%. And monotonic increase, decrease here was only 68%. And here even worse. So trying to show these variations along a dimension of a concept reveals a lack of understanding of particular concepts in this space. And so in systems that are so, prone to learn shortcuts, I think it's really important to probe them, to probe for their understanding, their ability to do actual general, say, abstract reasoning. So in general, deep learning approaches have a number of limitations on these abstraction benchmarks. As I mentioned, they require a large corpus of training examples, so you need to generate them automatically, which can make the data sets susceptible to these shortcuts. And this procedural generation makes them less interesting. They're constrained to have certain primitives and certain ranges of size and color and so on. The original Raven set actually was a lot more interesting, but very small compared to the tens of thousands of examples. And none of these systems would be able to solve problems on the original set. The trained networks are not at all transparent. What did they learn? And again, from deep learning approaches, typically they rely on this kind of multiple choice answer generation. They don't generate their own solutions. And finally, if the goal is human-like abstraction abilities, it really doesn't make sense to have to train on tens of thousands of examples. When Raven gave his problems to people, they weren't trained on the system, on the domain. They were doing really zero-shot solutions. they were trained on, these problems were meant to test abstraction abilities in general that people had learned throughout their lives. And so it really doesn't make sense to have to train a deep neural network to on a very large corpus to be able to do these problems. Really, the essence of abstraction analogy is few-shot learning. So let me tell you a little bit about a different architecture. This is one that I developed with Hofstadter that actually addresses many of those limitations I listed above. This is old work, but I think it is has a lot of potential for applying these kinds of ideas now. So we looked at a different kind of analogy on these, an idealized domain using letter strings. So analogy problems like if the string ABC changes to the string ABD, what does the string PQRS change to? Well, there's no sort of formal description here that requires a single answer, but most people will say PQRT. They'll say, okay, the rightmost letter changed to its successor. So we'll do the same thing here. But then, if you can complicate that by putting in groupings of letters, where if you want to, instead of changing the rightmost letter to its successor, most people will here change the rightmost group to its successor, saying, okay, a grouping of letters plays the role of a single letter. And you can also look at problems that reverse strings or ask to sort of fill in a sequence, missing letters. And it's a very open-ended domain, even though it's, superficially looks very simple. We think of these as idealized situations that have objects, relations, groups, events that happen, things change. And it's really meant to be a tool for exploring general ideas of abstraction and analogy. The architecture we developed called Copycat was inspired by ideas from neuroscience and psychophysics. For instance, the ideas of Anne Treisman, who looked at the dynamics of perception. That is, perception isn't just a feed-forward process like in a neural network. It's a dynamic process where your eyes move around and there's feedback that when you see one thing, that causes your eyes to look in another specific direction. And there's, Treisman showed that there's a shift in perception between what she called pre-attentive processing, which is parallel, very, very random, bottom up, and more deterministic, focused, more serial, attentive top-down processing. There was also work in neuroscience that emphasized the importance of sort of working memory, even in the visual system, where the early areas of the visual system are sort of like blackboards in which you can store temporary information, and there's interaction between what's stored on the blackboards and what's being processed in higher areas. And finally, the notion that there are temporary data structures in this working memory which interact with longer term memory. So our project, the Copycat architecture, had this kind of working memory we call the workspace, in which the problem was stored and the system was able to build these kinds of data structures that were the result of computations in higher areas, the more permanent network of concepts, and were created by what we called perceptual agents or codelets, small pieces of code that could build small data structures like a grouping of letters or another grouping or a relationship between two letters or a correspondence across strings. So this was meant to model this kind of view of how perception works in a very dynamic way. It was controlled, all of the processing was controlled by a temperature. When the temperature was high, these agents would perform very randomly, but as they built structures, the temperature would lower. And so it was a feedback. The temperature was feeding back between creating randomness in the workspace and being lowered to become more deterministic as structures are built. So let me show you a little video of this program running. Oops, didn't want it to start yet. So what you'll see here is these agents making explorations. And notice this is happening over time. And when exploration yields some kind of possible relationship, that feeds back. You can see the temperature lowering. You can't see the concept network in this demo, but you do see the workspace. And you see these little agents building these structures that produce feedback among each other. So now this notion of grouping according to same letter catches on, and the whole the fact that this is a sequence of letters that's been perceived as a sequence of letters feeds back to make this more likely to be perceived as a sequence of letters. The system is able to parse it to describe this as reverse direction of string, and to translate that according to the fact that single letters go to groups of letters as reverse direction of the group. So that's an example of the program at work. So importantly, analogy making is seen as kind of a perceptual process. It might be in the mind's eye, where representation is actively built over time. Again, a dynamically integrating more symbolic conceptual knowledge with sub-symbolic probabilities and top-down, bottom-up processes, and a continual interaction of prior knowledge from the permanent concept network with more bottom-up perceptions and context. And like in Andreessen's work, we see in this system at the very beginning, a very bottom-up, more parallel random explorations taking place by these agents. But as the program starts to make sense of what's going on in its input, it shifts to a more top-down, serial, and deterministic mode of processing. And that transition is emergent, it's not programmed in. Now, Copycat itself has a lot of limitations. Its architecture is fairly ad hoc. It works on this letter string domain, but could the architecture be expanded to other more complex domains? It has been to some extent, but it's still not clear how general the architecture is. I personally think it's quite general, but that remains to be seen. It doesn't learn. So the question of how to form new concepts beyond what's given in its repertoire, what humans have given it. It has a repertoire of concepts and it uses them to build representations of a new analogy problem, but it doesn't learn new concepts. So let me finally talk about one last domain, which I think is really interesting. This was proposed a few years ago by Francois Chollet of Google, called the Abstraction and Reasoning Corpus, or ARC. He proposed it in a paper in which he said that we need domains in which to really compare machines and humans in a fair way that don't use language that we can overinterpret or anthropomorphize, and also only require a very few shot learning, and are based on what Elizabeth Spelke has proposed as our core knowledge systems, the idea that we are sort of innately given notions of objects, of space, geometry, numbers, numerosity, agents, and actions. So that's how Chollet formed his problems, thinking about these concepts. So here's an example, what he calls a task. The task has 3 demonstrations. These are kind of like in the letter string analogy, ABC goes to ABD. Here, this grid gets transformed into this grid. Similarly, this grid gets transformed into this grid, and so on. And now here's your test example. So you have 3 sort of training examples, if you will. And now I give you a test and say, do the same thing, generate the new grid. So you have to generate the answer. And you can see that, the concept is sort of take this idea of horizontal array of colors versus vertical array of colors. And humans can see that very easily. But the challenge is to get a machine to know enough about the core concepts that have been proposed for human knowledge to be able to apply them in this domain. Here's another example. We can see easily this is like extend this structure to the boundary using the different color here. This one uses the idea of a stripe of colors being above another stripe and then switching the above versus below. And here kind of locating a similar or the same shape. So here we locate that shape to get that and so on. So Cholet created manually what he called a training set, which is 400 tasks, just to give people an idea of what the different concepts are, and then an evaluation set in which they could use to kind of test their programs. And then finally a hidden test set, an evaluation set of 200 tasks that people didn't have access to, but they could submit their program to test it. And this was put on the Kaggle website, which gives machine learning challenges, $20,000 prize money for solving it to a certain degree. And the best programs were able to solve about 20% of the hidden test cases. And they each were given 3 guesses. So it wasn't just one guess like a human might have. So still these programs were not very general, and they're still not doing very well. There was an entertaining blog written by one of the authors of the second place challenge. We obtained the code for this, and we did the same kind of concept-based evaluation of that program that we did for the Ravens problems to sort of interrogate how well this program understood concepts on some of the problems that it succeeded on. So we looked at 2 kinds of concepts, one that involved top, bottom, or above, below, and one that involved interacting with a boundary. So just as an example, here's a problem from the original ARC data set that this program was correct on, extracting the color of the line that is above all the other lines. But then we looked at some variations on that, extracting the object or that is above all the other objects. It was not able to do that. Moving one object below another object or above, I'm sorry. It was not able to do that. Here's another one on the boundary where all the little two square objects move down to the line, down to the boundary or over to the boundary. It was correct on that one, but not correct on several variations that we tested it on. And I won't go into the details here. And so what we found was that while its performance on the original ARC test set was 19%, it actually did do slightly better on our variations on top bottom, but much worse on our variations on boundary. So we were able to interrogate how well it understood certain concepts. This was really a pilot study. You can see there's not very many examples. So right now we're extending this. So to finish up, the big question is, how do we make progress on this really important set of abilities that underlie human intelligence, that underlie our robustness? And this is from a paper I published recently. I believe rather than people having all these different tasks, like the letter string analogies, the Ravens analogies, the arc problems, we really need a common suite of tasks. And the ability to show that a program can do this kind of abstraction across different domains. I think these idealized domains are really useful. We can be very explicit about the prior knowledge and assumptions, and we can avoid anthropomorphizing language-based tasks, which we've seen happen again and again. We need to evaluate our systems not only on accuracy, but on generality across different tasks, like I've shown, and the ability to generate rather than simply recognize solutions. The ability to do few-shot learning or few-shot abstraction. Robustness to modifications, like the concept-based evaluations I showed, and being able to scale to more complex examples. So we should rate systems on all of these different factors rather than just accuracy. Okay, so I'll stop there and happy to answer any questions or hear your thoughts. Thank you.
Excellent. Thank you so much, Melanie. So let's open for question and answer. One question relating to what you said on Cholet's arc. Benchmarks seem like a huge driver in the field. So one question, would a copycat style letter string benchmark be a good idea or maybe not? And do you see other drivers or incentives, maybe coming from applications or from theoretical interests?
I think that we need, I think these idealized benchmarks are useful, but that people shouldn't just focus on a single one of them. They need to focus across different benchmarks, sort of like the way the natural language processing community is focused on multitask benchmarks, like if you're familiar with the glue and super glue benchmarks in language processing, that you're rated on like how well you do across different tasks, not just a single task. And I also think we have to, obviously these idealized benchmarks have limitations, and, the ultimate goal is to use these systems on real world examples and real world tasks. So you have to kind of be able to go from developing systems that can do abstraction on these more idealized problems to more real problems. But it's a way to, get started without having to deal with all of the complexities of the real world.
Okay, here is a question from Rahul Siripurapu. You distinguished between perceptual categories and concepts. However, it seems that concepts are not always timeless, like the concept of logism. Would you say that perhaps at some point in the future, only a few concepts from today may survive, with others being classified as perceptual categories?
Concepts is a very wide category, if you will. We have kind of everyday concepts that we use to understand the world that are probably pretty robust. And then we have more temporary concepts that we use to, in science, for example, that get thrown out when we understand the science better. Phlogiston and the ether and all of those are examples, but maybe, some people have proposed that, the things that we describe our mental states with, like consciousness, might actually be one of those concepts. So I think we're here in AI, we're talking about even just the most ordinary common sense ideas that are hard for AI systems to grasp. I think those will be around for as long as humans are.
There is a question from Ivan Shvogor. Thank you for this great talk. It points out the curious problem in AI, and learning concepts is really an area that requires more exploration, but also understanding. It should be increasingly important to understand what the models really learn under the hood. So his question, should we make us focus on what machines learn? But do you see how can we bring that down to the level of engineering models? So in your view, how should the models look? Should we maybe even move away from backprop-based approaches?
Yeah, my personal view is that the current approaches like deep neural networks and trained with many examples using backprop or whatever are limited, and that we're going to have to move beyond those. There's lots of proposals for sort of hybrid symbolic neural AI. Some of them may end up not working very well, but it does seem like we have to capture something like the symbolic processing that it seems that people behave, and perhaps we'll be able to do that eventually with neural networks, but it doesn't seem like we can do that right now. So yeah, I mean, that's a big question, is how far can these backprop approaches go?
And another question, while looking at the copycat architecture, you mentioned this workspace idea of competing agents. This looks very appealing, very natural from a human perspective. Well, we have competing inner drives. Can you comment on the work that is currently being done in ML using this idea, what it achieves, and what you see maybe as the next achievable steps in this area?
So by this area, I wasn't sure exactly what that meant.
There's a paper you refer by Golay, which refers to this idea of workspace.
Oh yeah, having a workspace. Yeah, I mean, I think this idea of kind of having a working memory, in which you can represent objects and instances of objects and so on. That's part of a lot of different cognitive architectures that people have proposed, but I think that approach has lately, people are trying to do that within the deep learning framework, and it hasn't worked out so well. So I don't think there's a lot of work in that area. And I think there should be more. This is something that is in more cognitive models than in AI systems to date.
Excellent. Thank you so much for an amazing talk and an insightful discussion. Thanks everyone for joining, and looking forward to the next talk in our seminar series, which will be announced on the IRI website. Thanks again, and have a nice evening or day wherever you've been joining us from. Bye for now.
Thank you.